Hello, welcome back. This is episode 8 of Everything You Need to Know About JPEG. In today's episode, we are covering Chroma Subsampling. So let's not waste any time. Let's just jump right into it. What is Chroma Subsampling? If we look at a single color component of an MCU, each one of these values represents a color intensity at a specific location in the image, and each one of these values is also called a sample. So subsampling, or also sometimes called downsampling, means reducing the number of samples across an MCU. And specifically, we're talking about chroma subsampling because it is usually only the chrominance data that gets downsampled like this. So for the luminance, you will typically always have all 64 luminance samples. But the chrominance data can get downsampled to save space. We've already talked about this idea a little bit, that our eyes are more sensitive to subtle differences in luminance than they are to subtle differences in chrominance. What this means is we don't want to subsample the luminance because even though that would give us some space savings, it would very badly damage our perception of the image. However, we can get away with subsampling the chrominance data because that gives us a lot of space savings and we don't perceive all that much of a difference when looking at the final image. So how is the chroma data actually subsampled? Well, by default, there is ordinarily 8 samples horizontally and 8 samples vertically. So the sampling can be reduced in the horizontal direction or in the vertical direction separately. The actual JPEG standard doesn't specify what your options are as far as all the different ways that you could downsample. So really the options are kinda endless. However, the industry as a whole has settled down on 4 options. And I've briefly mentioned this before, but the most common file format that uses JPEG compression is the JFIF file format, the JPEG file interchange format, and the JFIF specification limits the chroma subsampling possibilities to 4 options. Like I said, in all 4 cases, the luminance data is unaffected, so there will always be all 64 coefficients for each luminance component. In addition to that, the 2 chrominance channels are always altered in the same way. In other words, the subsampling that is applied to one chrominance channel is always applied to the other. So what are those 4 options? Well, the first option is the one that we have been using this whole time up to now, which is no subsampling. In other words, all 3 components, the Y, the CB, and CR, in a single MCU are always made up of 64 samples. The second option is that the sampling factor for the chrominance channels is cut in half in the horizontal direction. Basically, instead of having 8 columns of values, the whole MCU component is only made up of 4 columns of values, and then those 4 columns are stretched horizontally to cover the whole width of the component. We'll see that in more detail in a few moments. The third option is the same idea, but vertically instead of horizontally. So a component for one of the 2 chrominance channels is made up of 4 rows of samples, and those 4 rows are stretched down to cover the whole height of the MCU component. In both of these cases, the total number of coefficients that need to be stored in the Huffman coded bit stream for the chrominance channels are cut in half. And you might have been able to guess this, but the fourth option is that the sampling factor is cut in half in the horizontal and vertical direction. And this is often called chroma quartered subsampling. So in this case, the values need to be stretched vertically and horizontally to cover the whole MCU component. Let's go ahead and take a closer look at these 3 scenarios so it makes a little more sense exactly what I mean by stretching the values. So like I said, in the case of horizontal subsampling, we will only have 4 columns of samples, and these 4 columns will have to be stretched horizontally to cover the other half of the MCU component. Well, basically, imagine each column of values taking up 2 columns wide of the component. So this first column will be used to populate the first 2 columns of the component. Basically, this value will get copied here, and so on for the whole column. Since this column of values occupies these 2 columns, the second column of real values will occupy the next 2 columns. So this column of values will get put into this location in the MCU component. And you probably get the idea by now. The third column of real values will go into the fifth and sixth columns, and the fourth column of real values will go into the seventh and eighth columns. And I'm sure you get the idea that it would work basically the exact same way with vertical subsampling. The first row of values will occupy the first two rows of the component, the next row of values will occupy the next two rows, and so on. So then the last scenario is when the sampling is cut in half horizontally and vertically. So instead of having 64 values in an 8x8 matrix, we'll only have 16 values in a 4x4 matrix. So basically, we only have these 16 values, and this corner needs to get pulled to the bottom right corner of the component. So this value would be pulled to the bottom right corner, and it would be stretched to occupy a 2x2 region. This value would occupy this region, the value in the top left would occupy this 2x2 region, and you could fill in the rest. So this is pretty straightforward, but it does create some questions, like how do we read just 16 coefficients during Huffman decoding when trying to extract the MCU components? Well, the answer, surprisingly, is actually that we don't just read 16 coefficients. When performing Huffman decoding to extract all of the values to put into an MCU component, we will always read 64 values at a time. Always. However, if there is downsampling in the image and we use Huffman decoding to read 64 values, those values will get stretched across multiple components as necessary. So if we're in the middle of Huffman decoding and we're decoding a chrominance channel on an image that uses horizontal subsampling, we will still read 64 values, but because of the horizontal subsampling, the first four columns need to get stretched to cover the whole MCU component. So what do we do about the next four columns? Well, those four columns will get stretched across the entire width of the next MCU component to the right of the current MCU. These four columns get stretched to account for this entire component, and these four columns get stretched to cover the entire width of the next component. Now that does answer some of our questions, but it creates even more questions too. Like, what order then do we read all of the values for each component for each MCU? Well, first let's think about the order for no subsampling. When beginning Huffman decoding and reading all of the DCT coefficients out of the Huffman coded bit stream, we first read all 64 coefficients belonging to the luminance channel of the very first MCU. Then we read all 64 blue chrominance coefficients that belong to the same MCU as the luminance data we just read. And then we read all 64 CR component values for the same MCU. Once we have all 64 values for all three components for the first MCU, we repeat this all over again and read the second MCU, the third MCU, and so on in the exact same way. This should be very straightforward. This is exactly what we've always done, but how is it different when we're using horizontal subsampling? Well, here's the trick that makes it all work out nice and cleanly. We start by reading all 64 values of the luminance channel for the first MCU, but then instead of moving on to read the chrominance values, we read another set of 64 luminance values. Then we read 64 blue chrominance values, which, because the chrominance data is halved, these 64 values are enough to give us two full blue chrominance components. And same thing with CR. We read 64 CR values, which is enough CR data to cover two components. So with no subsampling, after one round, so to speak, we have decoded a single MCU, a single 8x8 block. However, with horizontal subsampling, after one round, we have decoded two whole 8x8 blocks, all 128 luminance values, and all of the halved chrominance data. To make sure this is really clear, let's apply this to an image that is 3 MCUs wide and 3 MCUs tall. So let's say we have this image that is 3 MCUs wide and tall, and let's think about the order that we have to read each component out of the Huffman coded bitstream. And let's also make note of then where do those component values go in the overall image. And again, for now, let's consider horizontal subsampling. As we just discussed, we read 2 blocks of luminance data, And I'll go ahead and number everything so we can keep track. So we read Y0 and Y1, and then we read a blue chrominance data block, and then we read a CR data block. And remember, every time we read an entire block of data, it is always 64 values. And as we just discussed, that when we do one round of decoding like this will give us 2 whole 8x8 blocks. So Y0 will go right here, and Y1 will go in the next MCU horizontally. The CB data will be used for both of the first 2 MCUs, and the CR data will also be used for both. So maybe you can see where this is going, but what happens for the next round of decoding? So we read another round of values. We can assume that Y2 will go here, but where does Y3 go? Well, Y3 actually goes right here. Because a single round of decoding gives us more than one MCU at a time, that means that this is basically our new minimum coded unit. We have always talked about an MCU as being an 8x8 matrix, but that's not really what the JPEG specification says. What it says is that an MCU is the minimum amount of data that shall be encoded at a time in the Huffman coded bitstream. So in the case of horizontal subsampling, a minimum coded unit is literally a 16x8 block. Just like we talked about in an earlier episode, how to handle images whose dimensions are not exact multiples of 8, we learned that we have to still use a whole number of MCUs for the width and the height of the image, but then simply ignore some of the last columns or some of the last rows in order to get an image that does have the exact correct dimensions. The same thing applies here. Because our minimum coded unit has a width of 16, we need to add padding to our image to bring its width up to a multiple of 16. Of course, when it comes to actually rendering the image, this all gets ignored. It's just that we have to follow through with reading it out of the Huffman coded bitstream. So the entirety of Y3 gets ignored. The left half of these blocks will be used for this 8x8 block, and the right half of these blocks will be used for this block that is ignored. It might appear wasteful to encode all of these extra coefficients into the Huffman coded bitstream, but the truth is this kind of unused padding should be an incredible minority of the overall data that needs to be encoded. And then this exact pattern would be repeated for the next 2 rows of blocks. Now, what about for vertical subsampling? Well, the order of the components that we read for a single minimum coded unit is the same, but where these get placed in the overall image is different. First of all, Y0 gets placed in the first 8x8 block. However, Y1 gets placed in the next 8x8 block vertically. Then CB0 and CR0 are used to stretch across these 2 8x8 blocks. So now, with vertical subsampling, our minimum coded unit is 8x16 rather than 16x8. Now this pattern will repeat here and here with Y2, Y3, CB1, CR1, and Y4, Y5, CB2, and CR2. Then when we get to this 8x8 block, we run into a similar problem like we did with horizontal subsampling at the end of the first row. Once we get to the end of the first column, we will still decode Y6 and Y7, and Y7 gets ignored. Then we decode CB3 and CR3, and they get stretched vertically across this MCU. And lastly, let's visualize what happens when using both horizontal and vertical subsampling together. One thing we know is that when the chroma data is downsampled horizontally and vertically, the chrominance data is essentially quartered, so we should have 4 times as much luminance data. And what that means is we read 4 blocks of luminance data first, and then we read a block of blue chrominance data, followed by a block of red chrominance data. So then where do each of these blocks get mapped to on our image? The 4 luminance blocks will get placed into the image in the top 2x2 region. So in this case, our MCU is 16x16. So Y0 will get placed right here. and we travel horizontally before we travel vertically. So y1 will go right here, followed by y2 and y3. And as you can probably figure out, CB0 and CR0 will both be stretched across this entire 16 by 16 region. It's starting to get a little cramped, but I think you get the idea. And this pattern to decode a 16 by 16 region of the image will be repeated here, and then it will get repeated here, and then it will get repeated here. So as you can see in this case, there is a lot of unused blocks. Because the original image is 24 pixels by 24 pixels, which is not a multiple of 16, the effective width and height need to be bumped up to the nearest multiple of 16 to allow Huffman decoding to work properly. If this image were actually 32 pixels by 32 pixels, then none of this would be wasted. We would still read the exact same blocks in the exact same order out of the Huffman coded bit stream and place them into the same location in the image, but because the dimensions would be 32 by 32, none of it would be wasted and the whole image would be rendered. So we've talked a lot about how subsampling affects Huffman decoding, but how does it affect other stages? Should any of the other stages treat these subsampled blocks any differently? And when exactly does this stretching happen? Well, the way I presented this was probably misleading, and it probably implied that we should do the stretching right after we read the values out of the Huffman coded bit stream, but that is not what we should do. Instead, when we read all of this out of the Huffman coded bit stream, of course we place the luminance values where we would expect them to go, but we leave the chrominance values at the top left of the overall MCU like this. So all of these 64 values and all of these 64 values should stay packed into the top left 8x8 region, and all of the other 8x8 regions that belong to this MCU should remain uninitialized. The reason for this is that we need to perform dequantization and inverse DCT on these 64 values at one time. These 64 values do not get stretched and then have inverse DCT applied on each region. We keep all 64 values together packed into an 8x8 block and perform inverse DCT just like normal. Before inverse DCT, these 64 values represent the cosine weight coefficients that we're used to, and then we perform inverse DCT to transform those coefficients into actual CB data or CR data. And then that actual color data needs to get stretched across the rest of the MCU when we perform the color conversion from YCBCR to RGB. So there we go. I think that is all of the core principles of chroma subsampling, but there are a couple more caveats that we'll discover as we try implementing this. So let's jump over to our code. So where to begin? Let's start by going to our header file and modifying our header struct a little bit. So far, for the most part, all of this data is stuff that we read directly out of the file and then immediately store it into a struct. In addition to these kinds of things that are read directly out of the file, let's add a couple more fields to the header struct, which are things that we calculate ourselves. For example, the height and width of the image in terms of MCUs as opposed to in terms of pixels, like the two fields that we already have. And all these extra fields that we add, I'll keep them here at the bottom to keep them separated from the basic details that are read from the file. Now, these two values will tell us how many MCUs are needed for the actual image's color data. But as we just discussed, with subsampling, we may need to pad an extra column of MCUs on the right or pad an extra row of MCUs on the bottom. So let's have two extra properties. So the real MCU height and the real MCU width will either be equal to the normal height and width, or they will be one greater. There's one more thing we want to add here that will make sense in a little bit, but we want to add the maximum horizontal sampling factor and maximum vertical sampling factor values to the header itself. Of course, these sampling factors are already stored in our color component structs per color component, but among all the color components, whatever the maximum values are need to be easily referenced in a couple places. So let's store them here rather than having to calculate the max value on the fly every time we need it. But like I said, that'll make more sense in a few moments. So now let's jump over to the rest of our code and figure out what we need to do to use these new fields and support subsampling. So first, let's go all the way back to some code that we haven't looked at in quite a while. When reading the start of frame marker, we read the height and width in terms of pixels from the file. As soon as we have these values, we can go ahead and calculate the MCU height and MCU width. And we do that just like before. While we're here, we can go ahead and initialize the real MCU height and width. And we can just make them equal to the plain MCU height and width for now. We don't know yet if they need to be incremented by 1 until we read the sampling factors for the color components. So let's go ahead and do that now. In the same function, still while reading the start of frame marker, we can scroll down to when the color components are handled. And in that for loop here, the sampling factors are read. Currently, this is all we do to validate the sampling factors. We check if either one of them is not equal to 1. Obviously, we don't want this check in here anymore if we want to support sampling factors. But as we just discussed, the 4 situations that we will support all involve the sampling factors being equal to 1 for the CB and CR color channels. What that means is horizontally and vertically, there will be one 8x8 block of CB data and one 8x8 block of CR data per MCU. So that actually doesn't change. That's how the CB and CR data worked before, and that's still how it will work now. Where things are different is with the luminance channel. So here we will have a special case for channel 1, or the luminance channel. But for the 2 chrominance channels, we will use the same check as before. For the luminance channel, the check to validate will be similar, except we want to error out if either sampling factor is not equal to 1 and not equal to 2. So instead of just checking against 1, we will error out if either sampling factor is not equal to 1 and also not equal to 2. So remember that our 4 possibilities are when there's no subsampling, which is when these 2 values are both equal to 1, when there's horizontal subsampling, meaning this value is equal to 2, vertical subsampling, when this is equal to 2, and of course, both horizontal and vertical subsampling when both factors are equal to 2. But in all of those cases, the sampling factors for both the chrominance channels must always be 1. Now that we know the sampling factors for the luminance channel, we can determine if we should increment the real MCU width or height. Just starting with the width, we need to increment the real MCU width if the horizontal sampling factor is 2 and the image's MCU width is odd. If the horizontal sampling factor of the luminance component is equal to 2, and the image's MCU width mod 2 is equal to 1, which is to say that the MCU width is odd, then we need to increment the real MCU width. And the exact same thing for the MCU height and the vertical sampling factor. Now, like I said a minute ago, we want to store the maximum sampling factors in the header directly, but we know that the maximum values will actually always be the same as the luminance factor values. Because if these 2 values, the horizontal and vertical sampling factor for the luminance channel, are either equal to 1 or 2, that means they will always be as large as the chrominance sampling factors or larger. So this is a little bit of a shortcut just based on the kind of sampling factors that we are supporting, but we don't actually have to do any kind of comparison to determine what the maximum sampling factors are. We can just trust the luminance sampling factors and store those from the luminance component into the header as the maximum factors. Obviously, if we were going to support any bizarre, non-standard sampling factor setup other than the 4 that we've talked about, this shortcut would not work. Now that's all of the change we have to make to the start of frame marker function. Now that that's taken care of, we can actually scroll way down past all of our marker reading functions and go down to Huffman decoding. Of course, we've been doing the calculation for the images, MCU height and width at the top of a lot of these kinds of functions. So now that this information is stored in the header, we can remove it from anywhere else that we calculate it. Of course, when it complains that these variables no longer exist locally, we need to replace them with the values from the header struct. But from here on out, we need to be really careful whether or not we want to replace these values with the image's MCU height and width or the real MCU height and width. In this case of allocating the MCU array, we definitely want to use the real dimensions because we need to allocate enough MCUs to pad in the case of subsampling. So we replace MCU height with header MCU height real, and we replace MCU width with header MCU width real. That's a bit of a tongue twister. Now it is important to make sure we don't break any compatibility with non-subsampled images while we're focusing on subsampled images. So remember that these real dimensions will be actually equal to the image's MCU dimensions if the image does not use any subsampling. The next thing we need to fix is this for loop right here. This is one of those cases where we used a single for loop with a single variable I to loop through our two-dimensional array of MCUs, rather than using a Y and an X separately, just because this worked well, but it's not going to work anymore. We need to replace I with two for loops, Y and X, based on the MCU height and the MCU width separately. The reason for this is that it's very important that we read Y, CB, and CR components in the exact order that they appear in the Huffman-coded bitstream. With no subsampling, and with this basic for loop using I, that worked well because we would go row by row of MCUs, left to right, top to bottom. But with the possibility of subsampling, as we saw in our diagrams a moment ago, especially with vertical subsampling, the order is not strictly left to right, top to bottom. So let's replace I with Y and X. And as you can see, this is turning into a big refactoring mess. Before I move on, I'll point out that instead of a simple Y++ or X++ to go up by 1, we go up by the maximum sampling factors. That's because this whole for loop decodes one whole MCU, and in the case of subsampling, an MCU's dimensions are not necessarily 8 by 8. An MCU's dimensions can end up being 16 by 8, 8 by 16, or 16 by 16, depending on the subsampling being used. Now remember why it's called an MCU. It is a minimum coded unit. It is the minimum data block that must appear in discrete whole amounts. There's no such thing as decoding a partial MCU. So in the event that our MCU's dimensions are greater than 8 by 8 because of subsampling, when we do decode an entire MCU here, we might move by more than just one 8 by 8 block in either direction. Now this does bring up yet another refactoring hassle, which is that the name MCU for this struct is no longer really appropriate for exactly the reasons that we're talking about. This struct would better be renamed to just something generic like block, because in the case of subsampling, an MCU could be larger than an 8 by 8 block, but our procedure of decoding, especially when it comes to dequantization and inverse DCT, still always only processes blocks, 8 by 8 blocks. So we don't want to change this struct to be dynamic or anything and actually match the dimensions of the MCU. We want to keep it 8 by 8, but then that means the name MCU is no good. Maybe I'll come back to this. I'm not fully decided. Maybe I'll update the name of this to block, but for now, let's carry on knowing that a true MCU will be composed of multiple of these MCU structs when subsampling is being used. Again, not to beat a dead horse, but we want to make sure we don't break non-subsample images. So in that case, the maximum sampling factors will be equal to 1 and 1, so these behave just like before. This only has any difference if they're not equal to 1. So now what to do with this I? Well, we should be very familiar by now that to switch from the 1 coordinate value, I, to the 2 coordinate values that are equivalent, we use the y times the width of a row plus x. And in this case, it's important that we use the real width because that is the true width of the row of 8 by 8 blocks. So what next? Well, we have this loop that loops through every color component to then decode that color component. But we actually need to potentially decode many luminance blocks before even moving on to the chrominance blocks. Now, the actual number of luminance blocks that we need to decode is the luminance channel's vertical sampling factor times its horizontal sampling factor. So when they are both 1, we just need to read 1 luminance block. When the values are 1 and 2 or 2 and 1, we need to read 2 luminance blocks. And when they are 2 and 2, we read 4 luminance blocks. Now it is important that we put the loop for the vertical sampling factor outside the loop for the horizontal sampling factor so that we place the values into the correct position in the MCU array. Again, here we have to replace I with y and x. Except notice that y and x, which are these for loops here, will be constant values for as long as this VH loop is running. That means as each luminance block is decoded, it is just placed into the same location in the MCU array, which is obviously not correct. Luckily, it's just a matter of adding V to Y and adding H to X. Again, when subsampling is not used, V and H will always be 0. But in the case of subsampling, this allows us to decode 8 by 8 blocks and then place them to the right or down and to the right of the current YX block. I should also point out that this is a case where we don't want to use the real MCU height and width, but we want to use the image MCU height and width for the Y and X loops, because in the case of subsampling, where we needed to pad with more 8 by 8 blocks on the right and bottom of the image, they will be taken care of by the V and H loop when V and H are equal to 1 instead of 0, because 1 will be added to Y and X. So that will be how those extra padded blocks are extracted from the Huffman coded bit stream and placed into the padded location in the MCU array. The only other thing I want to do to this function for now before we move on is that we used to have a loop for I, so then that's why we named this J, but now we don't have I anymore, so I want to rename J to I. Now this may look like it's terrible for performance because this used to just be 2 for loops, I and J, and now it's 5 for loops, Y, X, I, V, and H. But it's not actually going to be that bad for performance because we're really doing basically the exact same amount of work. I was split up into Y and X, but overall it's the same amount of iterations between them. And for non-subsampled images, V and H won't actually ever loop more than once, so it's kind of like they're not even there. So even though we added so many for loops, it's not actually like we've just increased the complexity or the runtime of this function, really. So the only real big task left is to do the stretching of the chrominance data during the color conversion to RGB. But before we do that, let's just go through some of our other functions that now need a little bit of refactoring. So to dequantize the entire MCU array, we know, just like before, we don't need to calculate the MCU height and width anymore. And this is really the same, but even simpler as before. I needs to be broken up into Y and X, and inside the J for loop, which I will rename to I after deleting I, inside the J for loop, we will have a loop for V and H. Again, V and H will almost always only ever equal 0, so it's like they're not even looping. And then given all that, we will dequantize each of those 8 by 8 blocks. So I'm not really going to go through it line by line because it's basically the same as what we just did for Huffman decoding. Again, it looks terrible because we just turned this into a quintuple nested for loop, but we're actually doing less work than if we left this function alone, because the way this is set up now, we will not waste time dequantizing the padded blocks for the chrominance channels, which was just a harmless waste of time before. And the same exact idea for inverse DCT. And because inverse DCT is a more expensive operation than dequantizing, it's actually more important that we add in this extra logic so that we skip performing inverse DCT on the padded chrominance blocks. So all that's left is to refactor the color conversion and implement the stretching of the chrominance data. But before we do all of that, let's actually just fix up the usage of the MCU height and width here. So we don't need to calculate it, of course. Instead of MCU height, we want to use header MCU height. And instead of MCU width, we want to use MCU width real. We'll come back and add the color stretching in a moment. The last bit of refactoring needed because of the change to the header struct is here in write BMP. Here we don't need to calculate the MCU height and width anymore. And then right below, we want to use the MCU width real. Okay, now before fixing the color stretching here with the color conversion, let's test the decoder out and see what it actually does with ordinary images and with subsampled images. So we have our usual 4 test JPEG files. To make sure we can still decode them correctly, we will make and decode all the JPEGs in the directory, and all the BMPs still look good. Let's make a folder called sub for subsampled test files, and here I will add 3 tests for now. They're all the same image, but one uses horizontal subsampling, one uses vertical subsampling, and this one uses both. Of course, they all look essentially identical. The good news is it ran without any errors, but let's take a look at what it produced for each of the tests. Here I'll just keep one of the originals on the side for comparison. And let's start by comparing it to the output of the image that uses horizontal subsampling. So as you can see, the luminance data is perfectly intact. There's nowhere where the brightness is missing or distorted. But horizontally, we're missing half of the color data. The color data that we do have, these columns here, need to be stretched horizontally to cover the gaps. It's really noticeable in areas like this on the fish's eyelid. You can see the slope of the orange is twice as steep as the actual slope of the brightness of the eye. If you imagine these 8 pixels being pulled to be 16 pixels wide, this point would be pulled straight out to here, and this steeper slope would be flattened out to match this slope. Let's take a look at the BMP with vertical subsampling. And you probably could have guessed it's basically the same thing, except each row of color data needs to get pulled down vertically. Here, what is interesting with the eye is that this orange isn't even touching the eye at the moment. But when these 8 pixels are pulled down to cover 16 pixels in height, then this orange will cover basically the bottom half. And this blue portion will be pulled down to cover this entire height. And lastly, let's look at the image that uses both horizontal and vertical subsampling. Now, I just think this looks incredibly interesting. Of course, we have 8 by 8 squares of color that need to get pulled to the right and down, and also down to the right, to cover a 16 by 16 region. So now I hope it's clear why this is called chroma quartered. We quite literally only have a quarter of the original color data. Remember that during Huffman decoding, we first decode the luminance blocks, in this case 4 in a row. First we would decode the top left luminance block, then the top right luminance block, then the bottom left luminance, and then the bottom right luminance. After all 4 of those in a row are decoded, then we decode one CB block and then one CR block. then move on to the next MCU. So let's finish this off with stretching the color data. Let's start by just refactoring this loop and replace I with Y, X, V, and H, similarly to before. But we do need to change this up a little bit. As it turns out, during this entire VH loop, we actually want to read from the same 8x8 block again and again for all of the CB and CR color data, specifically block YX. So we can set up that constant reference before entering the VH loop. So we want to use MCU YX for all of the CB and CR data during this loop. But based on the sampling factors, based on the value of V and H, we want to read from a different 8x8 block to grab the correct luminance data. This MCU, which depends on V and H, will give us the correct luminance data. So we need to rework the parameters that get provided to this function to account for both MCUs that we need to read from. First, let's just move this outside the function call to declare a reference to that MCU beforehand. So we know that we want to pass the luminance MCU and the CBCR MCU to this function, but we'll also need to pass the header and the value of V and H. And the reasons for that will become clear in just a minute. So here we'll pass the header, both MCUs, V and H. Now we can finally modify the actual color conversion function to account for the stretching. Let's start by replacing I, which goes from 0 to 63, with Y and X, which will both go from 0 to 7, but let's actually loop in reverse from 7 down to 0, because as you recall from our diagrams at the beginning, as we are duplicating columns or stretching columns to the right and stretching rows downward, we don't want to start from the top left and move our way right and down, because we will be overwriting values that we haven't yet stretched. So we actually need to start at the bottom right, and as we duplicate values, we can move left and up. We just need to guarantee that we never overwrite some chrominance data before we have stretched that chrominance data. And like usual, we'll replace I with Y times 8 plus X. And let's fix our parameter list. So instead of taking the MCU that needs to be processed, we'll take the header, the MCU that needs to be processed, which contains the luminance data, the constant reference to another block that just contains the read-only CBCR data, and the current V and H value. Now, as we pull in this luminance data and this CBCR data, the output goes back into this MCU. So even though we've changed basically nothing so far, we're actually almost done. The only thing we have to do is, when reading the CB or CR data, don't read from this MCU. Read from this MCU instead, and of course read from the correct coordinates inside that MCU. So let's try to figure out the correct row number or Y coordinate and the correct column number or X coordinate that we need to read from in the CBCR block. Starting with the row, usually this would just be Y, but in the case of vertical subsampling, the maximum vertical sampling factor will be 2, and then we know we're just trying to copy 4 of the rows of this CBCR block and pull those 4 rows to cover all 8 rows. So our Y index should only have 4 possible values, not 8. Currently, Y could be 0 through 7, but we need it to be 0 through 3. And we can achieve that by dividing by the header's maximum vertical sampling factor. If this value happens to be 1, then Y is unaffected. But if this value is 2, Y is cut. Its range is cut from 0 through 7 to 0 through 3. However, there are actually 2 scenarios, even in the context of vertical subsampling, that we need to be aware of. Either we are copying the top 4 rows of the CBCR block and stretching those, or we're copying the bottom 4 rows. That is based on whether or not the value of V is 0 or 1. If the value of V is 0, then this is all we need, because Y will correctly be 0, 1, 2, or 3. But if the value of V is 1, we actually need to add 4 to this value. so that instead of 0, 1, 2, 3, the possible values will be 4, 5, 6, or 7, so that we copy always from the bottom 4 rows when v equals 1. To do that, we can simply add 4 times v. If v is 0, we're adding nothing, and if v is 1, we're adding 4. For the pixel column, or the x value, it's basically the same thing, but we use x, the horizontal sampling factor, and h instead. Now that we have these coordinates, we can calculate the actual pixel index that we want to use from the CBCR block, which is the row times 8 plus the column. Then we want to use this pixel coordinate instead of this one when reading any CR value or CB value. And of course, we want to read from the correct MCU block to begin with. And that's it. Let's test it out. And let's see if that fixed it. And would you look at that? So that worked on the image that uses horizontal and vertical subsampling. It worked on the image that just uses horizontal. And it worked on the image that uses just vertical subsampling. Unfortunately, though, we're not completely done. Let's add one more test file. This is a copy of gorilla.jpg. It still uses restart intervals, just like our original Gorilla does, but now it also uses Chroma Subsampling. Let's see what happens when we run the decoder on this image. And it gets to Huffman decoding, but errors saying invalid DC value. That's not super informative, but basically what that means is it became totally desynchronized in the middle of the Huffman coded bit stream. Now you might be able to guess why that actually happened. If we go back to our Huffman decoding, here it compares if our MCU number mod our restart interval is equal to 0. However, because of the added confusion about 8x8 blocks, whereas MCUs can be bigger than 8x8, this actually represents the block number, but restart interval is supposed to be in units of MCUs. So to convert this from units of MCUs to units of 8x8 blocks, we can take the restart interval in terms of MCUs and multiply it by the maximum horizontal sampling factor and multiply it by the maximum vertical sampling factor, which converts this into a restart interval in units of 8x8 blocks. Now we can say if the restart interval, this local variable, is not 0, and our block index mod, our local restart interval variable, is equal to 0, now it is time to restart. So now let's see if we can produce the bitmap that goes with this JPEG file. And it finished without complaining. And if we look at the bitmap, it looks correct. So there we go. That is finally everything. Our decoder can now support all standard subsampled JPEG files. And all that's left is to handle progressive JPEG decoding, which we'll tackle in the next episode. Thank you for watching, and we'll continue this next time in episode 9.